This lesson is about axial rods in tension or compression. So I'm going to solve a problem right now that illustrates how do you combine compatibility and equilibrium in order to obtain the total deformation of interest. So we have two rods here, 1 and 2. And the length of the first one is 24 inches. It's a solid circular cross-section, 2-inch diameter. The second one is 18 inches in length, and it's a solid cross-section of 1-inch diameter. We're going to call this plane here, where the two intersect, plane 1, and this one here, plane 2. And if we look at this, the rods have a 5,000 load applied at the tip, and we are interested in the total deformation at this plane in section 2, right? We want to know how much that point moves up. And so to do that, we're going to break up the problem into two parts. We're going to look at this rod 1 and rod 2 separately, and then we're going to combine the results. So first, we will determine the deformation at this plane. We're going to call that delta 1. And because that force is constant throughout both rods, we can basically see that this rod is subjected to an axial force in tension of 5,000 pounds, right? The second rod, similarly, is also subjected to an axial load of 5,000 pounds, clearly. But we are going to compute delta 2-1, which basically means the deformation of point 2 with respect to point 1. So we're going to determine how much this moves with respect to this point. So the total deformation, delta 2, is going to be delta 1, how much that plane moves up due to the load, plus how much this plane moves with respect to that plane due to the axial load. So basically, we get that the total deformation, delta 2, is delta 1 plus delta 2-1. That is the deformation of this point plus the relative deformation of this point with respect to this one. The reason we are doing that is because these two deformations, delta 1 and delta 2-1, can be easily computed using the standard formula for axial deformation in rods with constant cross-section, constant elastic modulus, and constant load. It's PL divided by AE. P is the load, L is the length, A is the cross-section, and E is the elastic modulus. For this problem, we are going to work with an aluminum rod which has an elastic modulus of approximately 10 times 10 to the 6 pounds per inch square. So let's go ahead and compute delta 1, which is going to be 5,000 pounds times 24 inches, which is the length, divided by A1, right? In this case, A1, because it's a solid circular cross-section, is pi diameter squared divided by 4. In this case, the diameter is 2, so 2 times 2 is 4, divided by 4, that cancels out, and we get an A1, which is approximately 3.1416 inches square. That goes in here, 3.416, divided by the elastic modulus, 10 times 10 to the 6. If you do that calculation, that comes out to 0.0038 inches. Delta 2 delta 1, 2, I'm sorry, 2, 1, which is the deformation of this plane with respect to that. So basically you fix this right here and you just find how much this moves with respect to that, and then you add how much that moves, which is delta 1. So delta 2, 1 is again 5,000 pounds times 18, which is the length, divided by the area of that rod, which would be A2. In this case, this would be pi times diameter 2 squared divided by 4. The diameter is 1 inch, so the answer becomes pi over 4, which is approximately equal to 0.7853 inches square. That comes here. Divided by the elastic modulus 10 times 10 to the 6, and you obtain 0.0115 inches. Putting those two together, using the compatibility of deformations, right? We get 0.0038 plus 0.115, and we obtain a final result of 0.0153 inches. And that is the final result for the deformation, at the total deformation at this point.